Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Daniel Kleppner and Robert J. Kolenko. Today we are going to discuss topics from Chapter 2, Newton's Laws. As you all know, classical mechanics is a branch of science which deals with the study of motion, and the foundation of classical mechanics is provided by the famous Newton's law. And there are three Newton's laws: Newton's first law, which is also known as law of inertia; Newton's second law, which is also known as the law of force; and the third law, which is known as the law of action and reaction. Newton's laws is not the only approach to study a classical mechanical system. There are also other approaches like Lagrangian and Hamiltonian formalism. In Newton's laws, the most important parameter is the force which acts on the system, which causes motion in a system. On the other hand, in the case of Lagrangian or Hamiltonian formalism, the most fundamental aspect is the energy, not the force. However, compared to other formalisms, the Newtonian approach is much more simple because the laws as such are very simple to state and they involve very little mathematical complexity. Most of the natural phenomena which we see in our daily life can be easily explained using Newtonian mechanics. However, there are situations where Newtonian mechanics fail. For example, if you want to study systems which move with velocities which are comparable to the speed of light. The speed of light is around 3 × 10⁸ meters per second. So at such very high velocities, Newtonian mechanics fails, and you will have to require new formalisms such as relativistic mechanics. Similarly, if you want to study systems whose dimensions are in the order of atomic dimensions or subatomic dimensions, once again the Newtonian mechanics fail here, and you will need new tools like quantum mechanics. So there are several phenomena in the universe which can be easily explained by Newtonian mechanics. For example, the planetary motion. On the other hand, other phenomena like motion of electrons inside an atom cannot be explained using Newtonian mechanics. But wherever applicable, Newtonian mechanics provide the easiest route to understand the motion happening in a system. Now, motion or rest, both are relative processes. You can say I am moving with respect to something, or I can say I am at rest with respect to something. Right? This is a relative definition. Now, what is the most fundamental step in studying the motion of a particle? Suppose I have a particle at a location P and I want to understand the motion of the particle. The first thing is to get a coordinate system or a frame of reference using which I can characterize the position of the particle. So the easiest coordinate system, depending on the symmetry, is the Cartesian coordinate system. So I have three axes, x, y, and z. Now I am going to define the position of the particle with respect to this coordinate system. And I call the position vector r as xi cap plus yj cap plus zk cap, where I cap, j cap, k cap are unit vectors in the direction of x, y, and z. I have bolded the letter here because this is the sign convention which will be used throughout the textbook as well as in my lectures. So whenever a letter is bolded, it indicates that this is a vector. Alternatively, you can also put a bar on top of a parameter to indicate that it's a vector. and usually when you write answers in your exam, you can follow that because it will be difficult for you to bold the letter every time. But in our textbook as well as in my course, a bold letter indicates a vector parameter. So once I define the position vector, now I can monitor whether the position vector is going to change or remain a constant with respect to this coordinate system. So a coordinate system is the most fundamental requirement to identify motion of a system. So such a coordinate system is known as frame of reference. So if you imagine a coordinate system attached to a rigid body and describe the position of any particle in space relative to it, then such a coordinate system is known as the frame of reference. So once you introduce the frame of reference and define the position vector, you can easily derive other parameter. So you monitor position vector as a function of time. So the derivative, the first order derivative of position vector gives you velocity. So velocity is dr by dt, or in terms of the Cartesian coordinate, this is dx by dt I cap plus dy by dt j cap plus dz by dt k cap. Or if you take the rate of change of velocity, this is known as acceleration. In terms of position vector, this is d square r by dt square. So once you get velocity, acceleration and position vector, you can derive all other parameters like momentum, force, etc. related to the system under study. Now, the choice of frame of reference is quite arbitrary. For example, suppose you have a moving train and a passenger is sitting inside the train and you want to study the motion of this passenger. You have several options. Either you can choose a passenger who is standing outside, so the passenger outside is at rest. You can fix a coordinate system on that passenger and study the motion of this passenger. So obviously, with respect to the passenger who is standing outside, this passenger is moving with certain velocity. Alternatively, you can choose another passenger who is sitting on the same train. You can fix a coordinate system on this passenger and monitor the motion of the fellow passenger. Since both these passengers are moving with the same velocity, if you are choosing this frame of reference, it appears that your co-passenger is not moving, right? Because both are having same velocity. So the choice is yours, and depending on which frame of reference you are choosing, the motion which you are going to measure is going to be different. As I said, if you are choosing a frame of reference which is outside, then you see motion in a different way. On the other hand, if you choose a frame of reference inside, then the motion is going to appear differently to you. So usually what people do is they choose a frame of reference which makes the analysis the easiest for them. Coming back to Newton's laws, Newton's first law, which is also known as law of inertia, it states that a body continues in its state of rest or uniform motion unless disturbed by an external influence. The property of the body that it cannot change the state of rest or uniform motion on its own is known as inertia, and the external influence which changes the motion is called force. I can illustrate inertia using an example. Suppose you have a glass, on top of that there is a piece of paper and a coin is kept on top of the paper. Now the coin is in a state of rest. Now if you pull the paper suddenly towards the right, the coin, it cannot change its state of rest on its own. In other words, it is governed by inertia. So as a result, the coin doesn't move towards the right, it just directly falls inside the glass. So coin cannot change its state on its own. There are three types of inertia. First one is known as inertia of rest. I'm sure you all would have experienced this at least once in your life. Suppose you are sitting in you're standing inside a bus and the bus is at rest. Suddenly, if the bus starts to move forward, what happens? You tend to fall backward. What's the reason? The inertia of rest is coming into picture here. When bus starts moving, the lower part of your body, which is in contact with the bus, starts moving in the forward direction, but the upper part, it continues to be in a state of rest. As a result, you tend to fall backward. Second one is inertia of motion. Once again, imagine that you are standing in a moving bus and suddenly if the driver applies a brake, the bus comes to an halt and you tend to fall forward. Here what's the reason? The lower part of your body, which is in contact with the bus, come to the rest position immediately, but the upper part continues to be in the state of uniform motion. Right? So as a result, you tend to fall forward. Another type of inertia is inertia of direction. Let's once again take the same example. Suppose you are standing in a moving bus, and if the bus suddenly takes a sharp right turn, what happens? You tend to fall in the opposite direction, right? Because your lower part of the body moves towards the right, but your upper part of the body continues to be in the same straight direction. So as a result, you tend to fall in the other direction. So these are some of the manifestations of inertia in our daily experience. Newton's second law, which is also known as law of force, states that the rate of change of momentum of a body is directly proportional to the force acting on it, and the change in momentum takes place in the direction of the applied force. So momentum P is defined as mass into velocity. Now, why do we require this particular parameter? When you study motion, motion as such is not only motion as such is important, the amount of motion is also important. For example, if I ask you to push a weight of 10 kg with a speed 10 meter per second over a distance 10 meter. Okay. I also ask you to push another object of 50 kg with the same speed 10 meter per second over the same distance 10 meter. Okay. Now I am going to stand at the other side and I am going to look at both the objects. Both the objects are moving with the same speed. Can I say that both the motions are same? Probably yes. Can I say that the amount of motion in both the cases are same? Most probably no, because the amount of effort required to create a motion in the case of a 50 kg object is much more than the amount of effort required to create the same motion in the case of a 10 kg object, right? So how do you characterize the amount of motion? That's where you require a parameter like momentum, which takes into account the motion as well as the amount of effort, which is the mass. Okay. So according to Newton's second law, the rate of change of momentum dp by dt equal to external force F. So I can substitute for P here. P is mv, so this is d by dt of mv. Mass is uniform or a constant. You can take it outside the derivatives. This is m into dv by dt. Rate of change of velocity is acceleration. So this is F is equal to ma, which is also known as equation of motion. Probably this is the most important step in analyzing motion of a system, writing down the equation of motion. Once you write down the equation of motion, F is equal to ma, or you can alternately write it as F is equal to m into d square r by dt square. As you notice, this is a second order differential equation. So most of the equations of motion which we are going to study in classical physics are second order differential equations. You can solve it, and when you solve it, you get the position r as a function of time. So this is what we mean by understanding the motion of a system. At a given time, I should be able to predict what is the position of the particle, right? So R of t gives you that. Now, from this definition, you can take a special condition where the external force acting on the body is 0. So ma equal to 0 or m into dv by dt equal to 0. Take m to the other side, you get dv by dt equal to 0, which means v is a constant. So what is the physical meaning of this? When no force acts on a body, the body continues to be in a state of uniform motion, which is nothing but your first law. So you can derive first law from the second law. Coming to Newton's third law, probably the most famous one, the law of action and reaction. For every action, there is an equal and opposite reaction. So if you have a wall and you push the wall using your finger, the amount of force exerted by the finger onto the wall, there is going to be an equal force in the opposite direction exerted by the force onto your finger. So you can see the manifestation of Newton's third law probably in every walks of life. For example, if you jump on a springboard, what happens? You are applying a force in the downward direction and the springboard applies an equal force in the upward direction. As a result of that, you are going to jump upward. Right? And if you take two bodies, body 1 and 2, which are interacting with each other, let F12 be the force exerted by body 1 onto body 2 and F21 is the force exerted by body 2 onto body 1, then according to Newton's third law, F12 equal to minus F21. So Newton's third law says that forces always exist in power. And later on in this course, you will see that as a consequence of Newton's third law, the linear momentum or angular momentum is conserved in almost all classical mechanical systems. Now coming back to the frame of reference or the coordinate system, there are two types of them. One is known as inertial frame of reference and the second one is known as non-inertial frame of reference. Inertial frame is unaccelerated frame of reference in which Newton's first and second laws hold good. So unaccelerated means the frames are either at rest or move with uniform velocity. Let's consider two inertial frames, S and S prime. So S has coordinates x, y, z and S prime has coordinates x prime, y prime and z prime. Let's assume that S prime moves with uniform velocity v with respect to S. So at time t equal to 0, their origins coincide. So after a time t, these two origins O and O prime are separated by a distance vt. Velocity is distance by time, so velocity into time gives you the separation distance. Imagine that I have an object, a particle at a point P. The position vector of the particle with respect to S frame, I call it as R. The position vector of the same particle with respect to S prime frame, I call it as R prime. As you can notice here, using the principle of vector addition, I can say R equal to R prime plus Vt or R prime equal to R minus Vt. So this is the relation between position vectors of these two inertial frames. Let's see what is the relation between corresponding velocity. Take the first derivative on either side, dr prime by dt equal to dr by dt minus v. V is uniform or a constant. So let me call dr prime dt as capital V prime and dr by dt as capital V. So the velocity measured in S prime frame equal to velocity measured in S frame minus the relative velocity v. So this is the relation between velocities measured in these two inertial frames. Moving on to acceleration, d square. Once again, take derivative on either side. D square r prime by dt square equal to d square r by dt square. V is a constant, so when you take derivative of that, it becomes 0. So call this as a prime, d square r by dt square as a, so you get a prime equal to a. So even though the position vectors and velocities are different on both the frames, the accelerations are the same. So I said these two are inertial frames and they move with constant relative velocity, or I can state in the opposite way. If a frame is an inertial frame, then all those frames which move with constant velocity relative to the first frame are also inertial. This is the first inference from this exercise. What is the second inference? Particle experiences same acceleration in two frames which are moving with constant relative velocity. Or you can say particle experiences same acceleration in two inertial frames. Since a equal to a prime, we know the equation of motion F is equal to ma, right? So the equation of motion or laws of motion are going to be same in all inertial frames. Suppose that you want to switch from one inertial frame to another. For example, you want to write x prime in terms of x or x in terms of x prime. This is known as transformation of coordinates, and in the case of inertial frame, you can switch from one inertial frame to another using what is known as Galilean transformation. Moving on to non-inertial frame of reference. These are frames in which Newton's law of inertia doesn't hold good. All accelerating and rotating frames are non-inertial. Let's first try to understand what's the problem if the frame starts to accelerate. Imagine that you have an object, a force is acting on the object so that it moves in the upward direction with an acceleration 10 meters per second squared. Now you want to study this motion using a frame of reference which is also moving in the same upward direction with the same acceleration 10 meters per second squared. So the object is moving with certain acceleration. The observer is also moving in the same direction with the same acceleration. Now when the observer look at this object, what does he see? Since both the acceleration are same, to the observer in this frame, it appears that the object is at rest. Right? Just like the case of two passengers moving on the same train. To this passenger, it appears that this passenger is not moving and vice versa. Right? So to this observer, it appears that the object is not moving, which means he will conclude that there is no force acting on this object, even though in reality there is a force acting in the upward direction. So there is a contradiction here. Similarly, assume that there is a particle at rest, which means there is no force acting on this particle, and you are trying to observe this particle using a frame of reference which moves in the upward direction with an acceleration 10 meters per second squared. So this is similar to the case of a passenger in a moving train. When he looks outside, the trees which are actually standing still, it appears that they are moving in the opposite direction. Same thing here. So to this observer, it appears that the object is moving in the opposite direction with an acceleration minus 10 meters per second squared. So he will conclude that there is a force acting in the downward direction, but in reality there is no force acting. So this is the problem with an accelerated frame or a rotating frame. Because of the acceleration of the frame itself, the acceleration you are going to measure is going to be different. Consequently, the force which you are going to measure is also going to be different. So if I call Fi equal to MAI as the force acting on a particle in an inertial frame, remember, whatever force you measure in an inertial frame is the true force. So Fi is the true force acting on a particle, but the observer in a non-inertial frame sees a different force Fn equal to MAN due to the acceleration of the non-inertial frame. Imagine that you have two frames S and S prime, where S is an inertial frame and S prime is a non-inertial frame. Assume that S prime moves with a uniform acceleration A0 with respect to S. Imagine that I have a particle at a point P. Let Ri be the position vector with respect to S frame, where the subscript I indicates inertial, and Rn be the position vector with respect to S prime frame, where n indicates non-inertial. Let's assume that the particle is originally at rest, or there is no external force acting on the point P, which means the force which you are going to measure from this inertial frame is going to be zero. Consequently, the acceleration you are going to measure from the S frame is also going to be zero. On the other hand, if you are in the S prime frame, remember S prime is moving with an acceleration A0 towards the right. So when you are going to observe the point P from the S prime frame, to you it appears that P is moving in the opposite direction with an acceleration minus A0. So the observed force in frame S prime is going to be minus MA0. So once again, minus MA0 is not a true force. Actually, this force doesn't exist. It appears only because of the acceleration of the frame in which you are making the measurement. Now, such a force which doesn't really act on a particle but appears solely due to the acceleration of the frame is known as fictitious force or pseudo force. So you can define fictitious force F0 as minus MA0, where A0 is the acceleration of the frame. Let's quickly see what's the relation between position vectors, velocities and acceleration. Now from this figure, you know this is Ri, this is Rn, and this distance you can derive using Newton's equation. You know distance S equal to ut plus half at square. If we imagine that the initial velocity is 0, then the separation distance is half at square. In this case, acceleration is A0, so the distance is half A0 t square. So Ri I can write as a vector sum of this distance plus Rn. So I write Ri equal to Rn plus half A0 t square, or Rn equal to Ri minus half A0 t square. We are more interested in the acceleration, so take the second order derivative, d square Rn by dt square equal to d square Ri by dt square minus A0. A0 is a constant, so it is not affected by the derivation, the differentiation. So if you call this as An and this as Ai, where An is the acceleration measured in the non-inertial frame and Ai is the acceleration measured in the inertial frame, and A0 is the acceleration of the frame. So you get An equal to Ai minus A0. Multiple either side with mass m. Now you may ask a question, the position vector is different in the inertial and non-inertial frame. The acceleration is also different in both the frames. Will the mass be different for both the frames? So there are two parameters which do not change when you change from one frame of reference to another frame. One is time and the second one is mass. So mass and time are invariant under transformation. There are situations where mass and time are going to vary. This happens when the frame starts to move with velocities comparable to the speed of light. But this is the realm of relativity, which is a completely different topic. So for most of the particles or most of the classical system which we encounter in our daily experience, the velocities are much lower compared to the speed of light. So for all practical purpose, you can assume that mass and time are invariant. So when I multiply An with m, I get force Fn. This is equal to Fi plus minus ma naught is the fictitious force F naught. So Fn equal to Fi plus F naught. So Fn is the force I am going to measure in the non-inertial frame, or this is the apparent force. Fi is the true force and F naught is the fictitious force. So I can write F apparent equal to F true plus F fictitious. Or alternatively I can write F accelerated equal to F inertial plus F fictitious, where left hand side is the force measured in the accelerated frame and this is the force measured in the inertial frame. So if you compare inertial frame and non-inertial frame, you can easily notice that in the case of non-inertial frame, the analysis is going to be much more tedious because your acceleration and force are getting manipulated by the frame itself. So whenever possible, if you have a choice, you can always choose an inertial frame to study motion. That's why in most of the cases, we choose Earth as the frame of reference, because we know that Earth is not moving, it is an inertial frame, and if you try to study motion with respect to Earth, your analysis is going to be more easy. But in the strict sense, Earth is not an inertial frame because you know that Earth is rotating, right? So we have defined that every rotating frame is a non-inertial frame. But when it comes to Earth, you know that the rotation speed of Earth is very, very small. The angular velocity is the order of 10 to the power minus 5 radian per second. So since the rotation speed is very small, for all practical purpose, you can assume that Earth is a stationary frame. Now, what are the implications of an accelerated frame, or what are the effects of the fictitious force? There are several effects. I am just going to highlight one interesting one. So probably you would have heard about zero gravity flights or weightlessness, right? So how do you achieve weightlessness? You board a plane. The plane is going to take you to a height of around 6,000 meters from the surface of Earth, and at a speed of around 800 meters per second, the plane is going to fly in a parabolic path. So in this path there are three portions. The first one is known as the pull-up portion, the initial steep path. So this is a picture of the pull-up portion. Then you have the parabolic portion, then there is a pull-down portion. So typically one parabola takes around 60 seconds and you are going to experience weightlessness or zero gravity during this portion from here to here for approximately around 20 to 22 seconds. So typically in a flight, they are going to carry out several parabolic maneuvers, typically around 40 to 45 maneuvers. So in each parabola, for a time duration of 20 seconds, the passengers inside are going to experience weightlessness. If you've not heard about zero gravity flight, you can just type it in your YouTube. There are several videos. One popular one is an episode done by Santosh George Kulangara in Safari channel, where over a duration of 3 or 4 episodes he explains in detail the zero gravity flight which he took in NASA. So it's a very interesting episode. Now let's try to understand what's the physics behind it. We are not going into the details of the physics, but at least we understand what is the fundamental principle here. So this happens primarily because of an accelerated frame. The passenger is sitting inside a plane and the plane is obviously accelerated, so the plane is a non-inertial frame. The plane is at an angle, so its motion has two components, one vertical component and a horizontal component. Obviously this analysis is more tedious, so for simplicity let's assume that the plane is moving vertically up and vertically down. Let's first check what happens when it is moving vertically down. Okay. Let's imagine that the acceleration of the plane is equal to acceleration due to gravity, which is 9.8 meter per second square. Okay. As I said, the plane is accelerating, so this is a non-inertial frame. So the force which you are going to measure inside, or the force which you are going to experience inside the flight, is the non-inertial force Fn, which is equal to Fi plus F0. Now what is Fi? Fi is the true force. What is the true force acting on the passenger? Even though you are at a height of 6,000 meters from the surface of Earth, still you are within the reach of the gravitational force. So the only real force acting on you is the gravitational force, and gravitational force always acts in the downward direction. By convention, downward direction is taken as the negative direction. So the true force acting on the passenger is m into minus g, or minus mg. Now, what is A0? A0 is the acceleration of the frame. Your frame is the plane. The plane is moving in the downward direction with an acceleration which is equal to the acceleration due to gravity. Downward direction is negative, so A0 is minus g. So the fictitious force acting on the system is minus ma0, which is plus mg. Now let's calculate what is the force that is going to be experienced by the passenger inside. So force Fn equal to Fi, which is minus mg, plus F0, which is plus mg, which is equal to 0. In other words, during a vertically down motion, the passenger inside is going to experience zero force, or is going to experience weightlessness. So this is the idea behind the weightlessness experienced by passenger during a parabolic maneuver. Now you can do this as an assignment. What happens when the plane moves vertically upward? So when the plane moves vertically upward, the acceleration of the plane is plus g, and you can substitute in this equation and see what is the final result. And from the result, try to understand physically what does that mean. So I just gave you this example just to highlight the fact that depending on the choice of the frame of reference, the motion you are going to measure or the motion you are going to experience is going to be completely different. In tomorrow's class, we will talk about some more information related to the non-inertial frame and fictitious force, and also we are going to see some of the applications of Newton's law. Now, in any science field, if you want to verify a theorem, you need to do an experiment. This is true for mechanics also. But one problem with the mechanical experiment is that is always going to be perturbed by unwanted forces. For example, if I want to study the motion of a simple pendulum, so I take a simple pendulum, pull it to one direction, or I apply an external force, and I want to study the oscillation happening in the system. But as you know, this oscillation is always influenced by the gravitational force as well as the frictional force, right? So clearly, from the point of view of the simple harmonic motion, the gravitational force and the frictional force are unwanted. Right? So wherever you perform an experiment on the surface of Earth or close to the surface of Earth, you are going to be influenced by gravitational force. So to overcome this, oftentimes physicists assume that the experiment is performed by an astronaut at an outer space. Now why do we do that? Because in outer space the effect of gravity is zero. So you can study what is the actual result of the applied force onto the system under study. So astronaut is one common example you are going to encounter throughout this textbook. So don't think that why on the earth we are choosing only astronaut for our examples. This is just to make sure that the omnipresent gravitational force is not affecting our analysis. Okay. So that's for today. Thank you.